Good morning, one and all. My name is Dr. D.V. Manjunatha, working as Senior Professor in the Department of Electronics and Communication Engineering, Alvas Institute of Engineering and Technology, Moodbidre. Welcome back to this session, 7th session of Basic Electronics, Module 2. We'll just recall what we did in the last class. So, we studied non-inverting operational amplifier or non-inverting amplifier, wherein we proved that the output voltage is proportional to the non-inverted version of input voltage. Therefore, the circuit was called as non-inverting amplifier. And we studied also the applications of operational amplifiers. Some of the applications include non-inverting amplifier, inverting amplifier, voltage follower, op-amp adder circuit, op-amp subtractor circuit, op-amp integrator circuit, op-amp differentiator circuits, etc. Then we have touched upon voltage follower circuit. What is voltage follower? Voltage follower is an op-amp circuit whose output follows the input voltage. And it is also called as a buffer circuit because it has very high input impedance and very low output impedance. Any circuit which has very high input impedance and very low output impedance is called as a buffer circuit. In electronics applications, we come across what is called as loading problems. Wherever loading problem is there in electronic circuits, we must do some impedance matching. To do impedance matching, we use a buffer circuit, which is usually a voltage follower circuit that we discussed. And it is a special case of non-inverting amplifier wherein RF, the feedback resistance, is made as 0 and the input resistance, that is, which is a R1, the resistance which is connected to the inverting input terminal of the operational amplifier in non-inverting amplifier, is made infinite. That's how we get a very high input impedance and very low output impedance for a voltage follower circuit. And it can be used as impedance matching circuit as a buffer in so many applications of electronics devices, electronic applications. Then we moved on to operational amplifier adder circuit, and we proved that operational amplifier adder output is proportional to the sum of the individual signals which are applied at the inverting input terminal, and of course we got a output with negative sign. That shows that it is a inverting adder circuit. So we stopped at that stage and we now move on to the learning outcomes of this session. That is, we will discuss some of the problems of operational amplifiers or the numericals of operational amplifiers. Then we will move on to subtractor little bit later. Then we will move on to integrator, op-amp integrator, then op-amp differentiator circuits. Next, let us take some of the problems on operational amplifiers. So here let me read out this problem. Determine the gain of the op-amp circuit shown below with RF is equal to 50 kilo ohms and R1 is equal to 20 kilo ohms. The circuit shown here is, we are applying a input signal to inverting input terminal of the op-amp through Rin. Therefore, it is called as a inverting amplifier circuit. So let me write this circuit and explain what is this. So the inverting amplifier circuit, we have, it is given. So this is a inverting amplifier circuit. This is minus, plus, positive terminal is grounded. To the negative terminal, we have called it as R in here, and we are applying the input signal here, and there is a feedback resistor RF, and the output is taken here. This is RF. In the given problem, they have given R1 or Rin. In this problem, they have given it as Rin, which is R1, which is equal to 50 kilo ohms, and RF feedback resistance, which is given to be 20 kilo ohms. So, we have proved yesterday V naught is equal to minus Rf by R1 times V in, and here V naught is equal to AF into V in with of course minus sign. So, what is AF here? AF is the gain of the amplifier, inverting amplifier, which is given by V naught by V in, which is equal to Rf by R1 or Rin. Here Rin, Rf and R1 are given. So, AF is given by gain with feedback in an inverting amplifier is given by Rf, which is Rf is given to be 20 kilo ohms. Rf is given to be 50 kilo ohms, sorry. This is Rf, okay, we will make it here 20 kilo ohms. Rf is given to be 50 kilo ohms. Therefore, 50 kilo ohms divided by 20 kilo ohms will give us the gain. So, AF is found to be 2.5. AF is found to be 2.5. So, this is the value of gain. Usually, the gain is represented in terms of dBs, decibels. We call it as decibels. Gain in dB, I will rub off this. The gain in dB can be written as gain in dB is equal to 20 times 20 log of AF to base 10. So, this is the gain. The formula for gain in dB is given by 20 log AF to base 10. So, AF we need to substitute it as 2.5. Therefore, gain in dB is equal to 20 log of 2.5 to base 10. You have to calculate what is the value of gain in dB. You have to calculate what is the value of gain in dB. Let us see what is the value. The value was found to be 7.95 dBs. You can see here the gain is given by R. The gain is given by Rf by R1, and which is found to be 2.5 without dBs. Usually, I have given one note here, which is a very important note. Usually, the gain is represented in terms of decibels. So, gain in dB is given by 20 log 2.5, 20 log 2.5. So, gain in dB is found to be 7.95 dBs, 7.95 dBs. So, we got gain in dB as 7.95 for this problem. Now, let us move on to next problem. So, problem number 2 on operational amplifiers. For non-inverting amplifier, given that R1 is equal to 10 kilo ohm, given that R1 is equal to 10 kilo ohms, and the gain required for the circuit is 91, determine the appropriate value of feedback resistor. So, here they have given the gain is found to be 91, the gain is given to be 91, gain is 91 here, and R1 is given to be 10 kilo ohms. So, here we have given R1, and we need to find out what is the value of RF. So, we know that the gain of the non-inverting amplifier is given by AF is equal to 1 plus RF by R1. So, RF is to be found out, AF is given, R1 is given. So, we can easily find out what is the value of RF. So, given R1 is equal to 10 kilo ohms, the gain is 91. Therefore, we know that AF is given by 1 plus RF by R1, which is equal to 91. AF is given to be 91, which is equal to here 1 plus is 1 plus RF by R1, RF by R1 is given to be 10 kilo ohms. Therefore, 91 minus 1, I will send this 1 this side. So, 91 minus 1 is equal to Rf by 10 kilo ohms here, Rf by 10 kilo ohms, which implies 90 is equal to Rf by 10, Rf by 10k. Therefore, what is the value of Rf? Rf is given to be 90 multiplied by 10 kilo ohms, 90 multiplied by 10 kilo ohms, therefore, it is 900 kilo ohms. So, for this given problem, AF is given, the gain is given. In the previous problem, we have seen RF and R1 was given. For an inverting amplifier, we found out the gain value. In this problem, it is a non-inverting amplifier and the gain is given here, and RF we need to find out, R1 is given. So, this type of simple problems will be asked for 2 to 4 marks in the exam. Please go through this type of problems, which is very easy, and you have to use the calculator, practice use of calculators to find out all these answers. Okay. So, with this we will move on to next problem. Next problem is problem number 3. Problem number 3, which is this one. So, find the gain and output voltage for non-inverting amplifier. Find the gain and output voltage for non-inverting amplifier using op amp when the input voltage is 0.5 volts and minus 3 volts. Consider the supply voltage as plus or minus 12 volts, and RF is equal to 10 kilo ohms and R1 is given to be 1 kilo ohms. So, when here in this problem, the value of output voltage, input voltage is given 0.5 and minus 3. Two cases exist here. In case 1, we have to take input voltage as 0.5 volts, and in case 2, we have to take V in or Vi as minus 3 volts. And in both the cases, he has given the supply voltage as plus or minus 12 volts, and the feedback resistor is given to be 10 kilo ohm, and R1, the input resistor or the external resistor, which is given to be 1 kilo ohms. So, let us see how to solve this problem. Now, solution. For non-inverting amplifier, we all know that the gain is given by AF is equal to 1 plus RF by R1, which is equal to V0 by Vi. So, let us consider two cases when Vi is equal to 0.5 volts. What is AF? AF is given to be 1 plus RF by R1, which is equal to V0 by Vi, Gain is always output voltage by input voltage, which is nothing but for non-inverting amplifier is given to be 1 plus RF by R1. So, we can take the formula for gain as V0 by Vi is equal to 1 plus RF by R1, or 1 plus RF by R1 is equal to V0 by Vi. So, we know that Vi is given, two values of Vi is given. So, let us consider the first case as Vi is equal to 0.5 volts, RF is given and then AF is given. So, how to find out V0? So, here V0 is given by, so what is that? AF is equal to 1 plus 10k by 1k is equal to V0 by 0.5. So, 1k by 10k by 1k is found to be 10, the value 10 plus 1 is 11 into V0 is given by 11 into 0.5. If you cross multiply this, you will get V0 is equal to 11 multiplied by 0.5, which is found to be 5.5 volts. So, it is well within the supply voltage limit. Supply voltage is plus 12 and minus 12 they have given. So, there is no cutting of the signal, clipping of the signal takes place. If once the output voltage exceeds, plus 12 volts, there will be clip off takes place. But here output voltage for this value of Vi is found to be 5.5 volts. Therefore, the output will be well within the supply voltage limit. Therefore, the output will not get clipped off. You will get 5.5 volts, V naught as 5.5 volts. Coming to second case, when Vi is equal to minus 3 volts, when Vi is equal to minus 3 volts, what is the value of V naught? We need to find out. So, again the same formula we can use, AF is equal to 1 plus RF by R1, which is equal to V naught by Vi. Therefore, AF is equal to 1 plus here 1 plus 10K by 1K, which is equal to V naught divided by minus 3. Therefore, V naught is equal to 11, which is same in the previous case also 11, here also 11, because gain is not going to change here. Only thing is we are changing the input voltage. Therefore, 11 multiplied by minus 3, which is found to be minus 33 volts. So, V naught is found to be minus 33.33 volts when the input voltage Vi is minus 3 volts. So, what is the meaning of this here? So, supply voltage he has mentioned. He has mentioned supply voltage in the problem as plus or minus 12 volts. Whenever the output voltage exceeds the supply voltage, there exists a clipping of the waveform. How exactly the clipping takes place, let us see on the board. Suppose this is the output voltage, let us say this is the output. Suppose this amplitude is less than minus 12 volts, then we will get the same signal, amplified signal without any clipping takes place. But on the other hand, if the voltage exceeds minus 12 volts, here in our case it is minus 33 volts for Vi is equal to minus 3. Therefore, the signal gets clipped off at this point, but we have to get the complete cycle like this, but we won't get this complete cycle like this. At exactly minus 12 volts, the signal gets clipped off, that means cutting off this portion takes place. Therefore, this is not a valid input, we can say. Vi is equal to minus 3 volts is not a valid input. Therefore, in the problem we have come across two cases. Case 1, Vi is equal to 0.5 volts, case 2, Vi is equal to minus 3 volts. So, case 2 does not exist here, because it exists, but we will get the distorted output. We will get the distorted output. So, we have to leave that if we come across such type of situations practically. So, we have to leave such cases. So, Vi is equal to minus 3 volts is not valid for as far as non-inverting amplifier is considered for this problem, right. Now, let us move on to next problem, or before that, what is the note which I am giving here. So, note for this problem, minus 33 volts is not possible, because output will be saturated at minus 12 volts. Hence, the remaining part of the waveform will be clipped off. That is what I explained. And let us move on to next problem, which is the fourth problem. So, determine the output voltage for the op-amp order circuit shown below. Determine the output voltage for the op-amp order shown below. So, what is the circuit? Let us see what is the circuit. So, this is the circuit which is given, op-amp order circuit. In the last class, we have seen this circuit. So, op-amp order circuit. Here, we are going to feed all the input signals. Here, we are feeding all the input signals. All the input signals to the inverting input terminal. Therefore, what is this? It is a inverting order circuit. Here, three signals are applied. One is plus 2 volts through the resistor R1, and plus 1 volt is applied through the resistor 1 kilo ohm, and plus 4 volts is applied through the resistor 1 kilo ohm, and the feedback resistor which is considered here is Rf is equal to 1K. This is Rf. Rf is equal to 1K. So, all the values are given, only a substitution. This type of problem is only just a substitution kind of problem. In that case, we need to remember what is the output voltage. So, output voltage in this case is given by minus Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. So, when we substitute all these values, we will get the output voltage. That is a very simple problem, but this type of problems are usually asked in the exam. So, let us solve how to solve this problem. Let us see. The output voltage V naught is given by, as I told you, it is minus of Rf by R1, this formula. This formula. So, V naught is equal to minus of Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. Here you can observe that in the given problem R1 is equal to R2 is equal to R3 is equal to Rf is equal to 1K. So, Rf by R1 get cancels, Rf by R2 get cancels, Rf by R3 get cancels. Therefore, the output expression reduces for this problem as V naught is equal to minus of V1 plus V2 plus V3. Therefore, what is the output voltage? Output voltage V naught is equal to minus of 2 plus 3 plus 4, which is minus 7 volts. So, the output voltage for this problem is minus 7 volts. You will be seeing this problem on the question paper. It is a very big circuit given. You may get confused. Don't get confused. The circuit is bigger, but the solution is very small. So, this type of problems are most commonly asked. Please go through all this type of problems. Next third problem, fifth problem given is design a scaling order. Design a scaling order circuit using operational amplifier to give the output. So, to give the output, this output we should get this output. For getting this output, what design we have to do? So, it is V naught is equal to minus of 8 V1 plus 6 V2 plus 5 V3. They have given this output voltage for a given circuit. Scaling order is this value. Design the circuit. When they give design the scaling order circuit means we need to find out what is the value of R1, what is the value of R2, what is the value of R3 and what is the value of Rf, right. So, this is the problem. So, the circuit given, so the scaling order we need to design. Since the output voltage contains the negative sign, you have to observe this. Since the output voltage contains the negative sign, hence this is a adder circuit, no doubt it is a adder circuit. You are adding 8 V1 plus 6 V2 plus 5 V3, but with negative sign, therefore it is a inverting adder circuit. Therefore, it is a inverting adder circuit. So, I have written here inverting adder circuit. It is a inverting adder circuit with 3 inputs, whose output voltage is given by, you must remember the output voltage expression of a inverting adder circuit which we have derived in the last class, which is V naught is equal to minus of Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. Let me call this as equation 1, and let me always you have to compare the given output voltage expression with the formula, then only you will get the values of Rf by R1. What is the value of Rf by R1? What is the value of Rf by R2? What is the value of Rf by R3? You will come to know. With that, you can try to find out the values and you can write the designed circuit at last, right. So, here V naught is given to be this expression minus of 8 V1 plus 6 V2 plus 5V3. Just compare equations 1 and 2. Compare equations 1 and 2. Comparing equations 1 and 2, we will see what we get, right. As I told you, we get Rf by R1 value, which is found to be 8 in this case, and Rf by R2 is found to be 6 in this case, and Rf by R3 is found to be 5. Here we do not know the value of Rf, and also we do not know the values of R1, R2, R3. So, we usually assume the value for Rf. Usually Rf values must be assumed in terms of kilo ohms, and it should be of several hundred kilo ohms. So, let us consider in this problem the Rf value as 100 kilo ohms. So, if we take Rf value as 100 kilo ohm, then the given expressions becomes in this case 100 kilo ohm by R1, 100 kilo ohm by R1 is equal to 8. So, which implies what is the value of R1? R1 is 100 kilo ohms divided by 8, 100 kilo ohms divided by 8, which is found to be 12.5 kilo ohms. So, you have to assume the value of Rf and find out the remaining values of resistors. Then we got, with the value of Rf is equal to 100 kilo ohms, we got R1 as 12.5 kilo ohms. Similarly, 100 kilo ohm by R2 is equal to 6, which implies 100k by 6, which is equal to 16.66 kilo ohms. 16.66 kilo ohms. R2 was found to be 16.66 kilo ohms. Similarly, Rf by R3 is equal to 5. Therefore, Rf we assumed is 100 kilo ohms. 100 kilo ohm by R3 is equal to 5. Therefore, what is the value of R3? R3 is found to be 100 kilo ohms divided by 5, which is found to be 20 kilo ohms. Then whenever they design the order circuit for the following voltage, if they give, you have to write the circuit diagram, and on the circuit diagram you have to mention all these designed values, all these calculated values. That completes the designing of the circuit. So, let us consider what is the diagram. So, this is the diagram. Therefore, the circuit with different values for the given problem is as shown below. Here we found out R1 as 12.5K. So, R1 we have applied here. Through R1, that is 12.5K, we are applying the input signal V1, and Rf is found, we assumed. So, usually 100K, 200K or 300K or 500K can be assumed as Rf values, especially for this type of problem. Several or some value of resistor which should be in terms of hundreds. So, let us say 100 kilo ohm for example, or it may be 200 kilo ohms, or it may be 300 kilo ohms. We can assume Rf values like this. And we found that R2 for this problem as 16.66 kilo ohms. With through this resistor we will apply the input signal 2, and R3 was found to be 20 kilo ohms, through which we will apply the input signal V3. Therefore, at the output we get what we get at the output? We get it as minus of 8V1 plus 6V2 plus 5V3. So, this is the designing of order circuit. So, whenever this type of problems are given, you have to calculate the values and insert all the values. Finally, you have to show that this is the designed circuit. Then only you will get a marks. So, let us move on to next application of operational amplifier. So, we have covered what we covered in the problems. We have covered the non-inverting amplifier problem, inverting amplifier problem, and then inverting adder problems. So, these three applications we have covered, problems on these three applications we have covered. we have some more applications like op-amp integrator, op-amp differentiator and op-amp subtractor. So, subtractor in tomorrow's class we will discuss, and today let us discuss with op-amp integrator. So, as the name itself tells you, it is an op-amp integrator. Integrator means it has to perform integration operation on the input signal. So, what is the integration of input? That will be the output of the integrator circuit. So, what is the definition? Let us start with the definition of an op-amp integrator. An op-amp integrator is a circuit whose output is the integral version of the input. The name itself tells you integrator circuit means the output should be the integral version of the input. Inverting amplifier means it is an amplifier whose output is inverted version of the input. Non-inverting amplifier means it is an amplifier whose output is whose output is non-inverted version of the input. What is differentiator? Differentiator is a circuit whose output is differentiated version of the input. So, like this you can remember the applications definitions very easily. The name itself gives you the definition. So, here op-amp integrator, an op-amp integrator is a circuit whose output is the integral version of the input. The integrator circuit looks like this. So, here we have considered the resistor R through which the input signal V in is applied to the inverting input terminal, and the capacitor is considered instead of resistor in the feedback path. We are considering the capacitor. So, what is the difference between inverting amplifier and inverting integrator? Only difference is instead of using resistor in the feedback path of inverting amplifier, we will be using the capacitor. If we use the capacitor, it performs integration operation. So, you can remember the integrator circuit as consider the non-inverting inverting amplifier. In an inverting amplifier, we are giving the input signal at inverting input terminal through the resistor R1 there, and RF in place of RF we will be connecting a capacitor. So, if we connect a capacitor in an inverting amplifier in place of feedback resistor, then the circuit becomes integrator, op-amp integrator. So, integrator means RC. Let us move like this: input and then feedback, RC integrator, CR differentiator, like that. Let us move on to what is the circuit details. The circuit details. So, when we go to circuit details, in op-amp integrator circuit, the input voltage Vn is applied to the inverting input terminal through the resistor R. That is what I told you. And similarly, what is the next point? The non-inverting input, the non-inverting terminal is grounded. The non-inverting terminal is grounded. That is what we do in inverting amplifier, right? So, non-inverting input terminal is grounded. The feedback capacitor C is connected between the inverting input terminal and the output terminal of the op-amp as shown in the above diagram. And also here, as we are giving the signal to the inverting input terminal of the operational amplifier, therefore, the op-amp in this circuit works in inverting mode of operation. Remember, whenever we give the input signal to the inverting input terminal, the op-amp works in inverting mode of operation. Whenever we give the input signal to the non-inverting input terminal, the op-amp works in non-inverting mode of operation. In some applications, we will be giving the input signals to both positive terminal as well as the negative terminals. Then in that case, the op-amp works in differential mode of operation. Now, let us move on to the circuit analysis for the integrator circuit on the board. So, as I told you, in an inverting amplifier, if I replace the feedback resistor by a capacitor, we will get an integrator circuit. And let me call this as R. So, this is the integrator circuit. So, very simple, inverting amplifier can be converted to integrator by just replacing the feedback resistor by feedback capacitor. Now, let us assume the current through R as IR, because it is a current through R, let me assume it as IR, and the current which is entering into the operational amplifier, we will call it as II, which is usually 0, we will see that. And let me consider this node as G. See, in these applications, in all applications, there are a lot of things which are repeating. So, repeating things you can remember for longer time, so that only a small difference whatever is there in a particular application, if you can remember, you can easily remember the op amp circuits, right. So, the resistance, the current through the capacitor, let me call it as IC. So, because current through C, I will call it as IC, current through R, I will call it as IR, current entering into the operational amplifier, I will call it as II. As usual, the analysis goes like this, circuit analysis. So, applying KCL, I told you very beginning, so many times I told, applying KVL, applying KCL and Ohm's law is very important, especially in this particular chapter or the module. Applying KCL to the node G. So, what we get when we apply KCL? IR is equal to II plus IF, II plus IC. Now, we know that we are using an ideal op amp here. For an ideal op amp, what is Ri? Ri is infinity. Therefore, what is II? II is 0. For an ideal op amp, one of the important characteristic is that input resistance is infinity. When the input resistance is infinity, the input current will be 0, almost 0 current it draws, the op amp draws. Therefore, what is the expression? IR becomes, IR is equal to IC. Let me call this as equation 1. Now, by applying Ohm's law, the same procedure follows everywhere in all the applications, same procedure is repeated. Therefore, we can remember this for longer time. IR is given by current through R. So, in this particular case, in this particular region, we have to apply the Ohm's law. So, applying Ohm's law to the circuit, we get VI minus VG divided by R is equal to IR. The current through resistor can be obtained as VI minus VG by R. Similarly, the current through capacitor. So, we need to find out IC. In order to find out IC, current through capacitor, we must remember this formula. C is given by, or Q is equal to C by V. We know this. C is equal to Q by V, sorry. C, capacitor is given by charge by voltage, Q by V. Therefore, what is Q out of this? Q is equal to, therefore, Q is equal to C into V. If I differentiate this, what happens? Differentiating this, if I differentiate this, we will get dq by dt, which is equal to C times, C is a capacitor which is a constant value, and voltage through capacitor is V. So, dV by dt. If I differentiate this equation, Q is equal to C into V, we will get dq by dt, which is equal to C into dV by dt. Therefore, what is dq by dt? Rate of change of charge. Rate of change of charge is nothing but the current I. Through what we are finding the current? It is through the capacitor. So, IC, capacitor current IC is given by C into d by dt of V. So, what is V in our circuit? What is V in our circuit? What is the voltage across the capacitor in our circuit? If we see the circuit diagram, the voltage across our circuit is found to be Vg minus V naught. Vg minus V naught, because the current is flowing in this direction. So, we must consider Vg minus V naught. So, V in our circuit becomes Vg minus V naught. Therefore, we can write IC for this circuit as C times d by dt of Vg minus V naught. So, this let me call it as equation 1, this is 2, let me call this as equation 3. So, let us substitute equation 2 and equation 3 in place of IR and IC in equation 1. We will get what we will get, let us see. Let me rub off this and write here. Therefore, IR, I will write Vi minus Vg by R, Vi minus Vg by R, which is equal to, what is IC? IC from equation 3, C into dVg by minus V naught by Vt. So, d by dt of Vg minus V naught. So, this one we got. Let me call this as equation 4, and we need to find out what is Vg. So far we have found out Vg by a concept called as virtual ground concept. Many times we discussed virtual ground concept. If we apply virtual ground concept for this circuit, whenever one of the input terminal is held at some potential, here it is ground potential, automatically the other input terminal is also pulled to the same ground potential. Therefore, voltage at node G is Vg. Vg becomes 0 by virtual ground concept, and as I was telling you, virtual ground concept exists only for the ideal op amp. Therefore, what is Vg in this case? Vg in this case is 0 because non-inverting input terminal is held at ground potential. Substituting Vg equal to 0 in equation 4, we get Vi divided by R is equal to d by dt of minus V naught. So, this is minus V naught. Now, this can also be written as, I will rub off this because we have taken all this. Let us rub off this, and what is this reduces to, this implies dV naught, okay, Vi by R is equal to minus d by dt of minus V naught. I can write it as minus d by dt of V naught. So, from this, if I cross multiply this, so we have left out with C, Vi by R, here C into dV by dt. We have got IC is equal to what? IC is equal to C into d by dt of V. V here is Vg minus V naught. So, we have to substitute here as C times d by dt of Vg minus V naught, C times d by dt of minus V naught. Here it becomes C minus of C minus C times dV naught by dt. Therefore, what is dV naught we will find out here by cross multiplication. dV naught is equal to minus 1 by RC. So, this C will come here, minus 1 by RC into Vi. We get dV naught as this one. So, what do we require here? We need to find out V naught. So, here differential version of V naught is there. So, whenever we need to eliminate differentiation, we have to take integration on both sides, because integration is a reverse process of differentiation and differentiation is a reverse process of integration. Therefore, applying integration or taking integration on both sides, what we get? Integration of dV naught is equal to integration of minus 1 by RC into Vi dt. We will get dt. Therefore, here dV naught was there, so it becomes dt here. So, if we take integration on both sides, integration of dV naught is equal to integration of minus 1 by RC into Vi dt. See here, d and integration cancels, because the both are reverse process. If we take integration, which is nothing but 1 by differentiation. Therefore, what happens? So, left hand side we get V naught, which is equal to minus 1 by RC is a constant. Let me take out 1 by RC. It is integration of Vi dt. So, you can clearly see this equation. Let me call this equation as star. If we clearly observe this equation star, here integration of input is taken care. Integration of input is taken and it is multiplied with some constant value minus 1 by RC. Therefore, V naught is proportional to, we can write V naught as V naught is proportional to integration of Vi dt. So, this shows that the above circuit works as integrator. The above circuit works as integrator. So, this is the analysis for integrator circuit, and first you have to write the definition, the circuit diagram, circuit details, circuit analysis, and finally you give the inference saying that equation star indicates that output voltage is proportional to integral version of the input signal. Therefore, the above circuit works as integrator. If you write this much, you will get nearly 6 marks. Usually this type of applications will be asked for 6 marks. So, that is what I did the analysis here on the board, on the PPTs. What is the inference? Equation star shows that output voltage of an integrator circuit is the integral version of the input. Therefore, the above circuit works as integrator. And what are the applications of integrator? The applications of integrators includes wave shaping. It will be used for converting some wave into another wave. We will see that later. Then it will be used in analog computers, and the integrator can be used for solving differential equations. These are the 3 important applications of an integrator. So, what we did today, let us recall at the end of the session, let us recall what we did. We did, let me go to this slide. We first discussed on the problems of operational amplifiers. We took 5 problems. All those 5 problems are typical problems which we have taken, which are very important from the exam point of view. Simple problems will be asked in the exam, and we just discussed op amp integrator. The op amp subtractor and op amp differentiator we will discuss in the next session. So, with this we will wind up this session, and thank you for listening to this class, and thank you very much.